Okay, now that we know how the C preprocessor can be used in order to define text expansion snippets and also to include files in order to create new kinds of files, we would like to understand how some of these things can be used in order to actually split a given project across multiple files, right. Now, the first thing we need to understand is why would I even want to do this, right, and this is related to a term that is usually called refactoring. And the idea behind refactoring is that if I find that there are certain kinds of code, let's say squaring a particular value or maybe computing a sum of squares of certain values, right, maybe I repeatedly want to find the distance between 2 points in a Euclidean space and I need to perform a formula like square root of x square plus y square or something like that. It probably makes sense to write a function in order to perform that computation, because that way I can reuse the same function. Now, why is that good? For two reasons. One is that the code itself gets shared, right? I only have one piece of code in one place in memory rather than having many copies of the same code in multiple places. So it sort of reduces the overall program size. But more importantly, it also makes it more resistant to mistakes, because I only have one place where I need to fix a bug if at all I find a bug in my function. So this whole idea of reusability of code is sort of the key behind this idea of refactoring. So splitting common code into functions is something that seems fairly intuitive and obvious. It also makes sense to take out common functions that are repeatedly used in many different contexts and split them out into libraries, right. So libraries are basically collections of functions that you might find are used by multiple different programs. The most obvious examples of these common functions are printf and scanf that we have been repeatedly using. But in addition to that, there are also many other things like square root and so on, which are available in the math libraries. And the moment you get into something sort of non-trivial and you need to write some kind of a thing which either interfaces with the operating system or with something else, let's say like the network or with a web server or any other kind of functionality, you will find that it probably makes sense to use an existing library that has been written and optimized by someone else rather than trying to write your own code. Okay. Basically, the point is that testing and debugging are much easier if you sort of focus on the contents of the library and just restrict yourself to what it is to what the library is expected to do. Now, as part of this business of refactoring into libraries, one of the things that turns out to be very useful is what's called a function prototype. Now, we already know what function prototypes are, right? If I want to use a function in some part of the code, I need to declare the function before it has been used. So there are two ways of doing it. One is that I could actually define the function and then in a later function I could use it, and C sort of implicitly takes the definition of the function as also the declaration of the signature, right. So this idea of what is a function signature becomes important at this point. Basically what it tells us is, I am calling a function. When I call the function, I don't just need the name of the function, I also need to know what kind of parameters it takes as inputs, right. And this actually is quite important. As we will see later, it is possible to do this without necessarily thinking about, without necessarily giving the right signature, and you will end up getting the wrong results. There are also a couple of more things that come in the context of multifile projects. In particular, there are two keywords. One is called static, which we have seen earlier when we declared variables inside a function as static. And you may recall that a static variable inside a function, what it means is that the memory allocated for that variable is not on the stack corresponding to that function, it is in the heap corresponding to the program, which means that even after the function exits, that particular variable continues to remain in the same place, right. So that is used in order to sort of survive across multiple calls to a given function, for example. The static in the context of multifile programs, on the other hand, has a very different meaning. It basically says that some particular variable is visible only inside a given file. Okay. And a related term is this keyword called extern, where it allows you to define a variable in one file and use it in another file. Now normally this would be difficult to do, right, because if I wanted to use a variable, I need to have a definition of the variable. I need to know whether it was an int or a float. But let's say that I define it in two different files, that becomes two different variables. Similarly, what happens if I try defining it in a header file and include it into both of those files? Remember what header files do, they just get expanded as text, which means effectively that I am defining the variable twice, once in each file. So the only way to really handle this is by using something called an extern declaration, as we will see with an example. So the example that we are going to take over here, and please ignore all the commented out lines for now, obviously they are there in order to demonstrate something later, right. But as we can see, I have one function out here that I am calling extfunc, which in turn calls another function called quad1, right. And if I go back and look through the rest of this main.c file, I'll find that there is no definition of quad1 out here, right. So you can of course go visit the replit, take a look at it, and confirm that there is no definition of quad1 out here. Quad1 is also not a standard function anywhere in C, which means that it basically doesn't exist at this point. Okay. On the other hand, I have another file out here which I have called arith.h, and let me just comment out this hash include arith.h out here, in which again ignore some of these other declarations for the time being. What I have is, I have one function out here called add, and I have another function out here called quad1, right. And the purpose of this was basically to show you that I could have another file where I have multiple different functions that are defined, and I would like to see if I can call this function quad1 that has been defined in arith.c directly from main.c. Okay. Now what actually happens behind the scenes over here is that if I try clicking on the run button, Replit will actually go through my entire project, find out all the .c files that are present over there, compile all of them into .o, we will get to that in a moment what that means, and then link them together into an executable. So interestingly enough, even though there is no connection as such between main.c and arith.c at this point, right, they don't even know that each other exists. Main is just trying to call a function called quad1, and it turns out that arith.c has a function called quad1. In fact, if you go hover over it, you will see that the the warning that Replit gives you is that implicit declaration of the function quad1 is invalid in C99. So normally one would expect that if something was invalid, it would be an error, but it turns out that in certain versions of C it is still not an error, it's only a warning. So Replit gives you a warning and asks you, okay, do you want to go ahead and fix it? Now it is usually advisable in certain scenarios to turn on all, you can actually turn on a flag in the compiler which says that any warning is actually converted to an error, and in general that's good practice, right, because it is never a good idea to ignore a warning that is presented to you by a C compiler, because you don't know what kind of problems it is going to raise later on. Anyway, let's see what happens out here, right. First we'll look at this function quad1. We know that what I'm performing, the computation I'm performing over here is b into b minus 4 into a into c, and then return minus b plus square root of d divided by 2a. So in other words, the first root of the quadratic equation, right. You will see that again implicitly declaring the library function square root, same problem comes up over there, and it keeps telling you, giving you warnings over here, but not quite telling you to correct them. Now let's see what happens when I actually run this. By looking at this code, it looks okay to me. I expect that given the parameters 1, 2 and 1, that basically corresponds to x square plus 2x plus 1. So x should, whatever I compute over here, should give me the value x is equal to minus 1, right. Let's see what happens when I actually run it. It prints out the value 0, okay. Now what happened, right? And what actually happens over here is, At the time of compiling the main.c, quad1 was just taken to be a function, right? And at this point, basically what it says is that you are trying to specify printing it out as a format, but as far as I know, quad1 is an integer, which is why this particular warning message has come up saying that the argument has type int. In other words, at this point in time during the compilation main.c, the compiler thinks that quad1 is a function that returns an integer, right? But it doesn't, right? After all, the definition of quad1 that we have over here is very clear. It returns a float. Okay, so what's going on? The point is, when I compile main.c, I have no knowledge of what quad1 looks like, which is why it ended up thinking of it as an integer, going ahead and compiling it, calling the correct function with the wrong parameters, getting back the wrong result, and trying to print it out as a float. The net result was that we were lucky that it at least ran without crashing, or probably unlucky because it didn't tell us that there was something wrong. How do I fix this? Relatively simple. All that I do is go and comment out the prototype, the function prototype that I have here, right? And if you look at it, you will realize that this is just the bare minimum prototype. All it's saying is quad1 is a function that takes 3 floats as input. I'm not giving them names, I don't call them A, B, C, and it returns a float, right? I could also have written this as something which says float A, float B, float C, and that's perfectly fine as well. The names A, B, C actually don't matter in this case. All that it cares about is what are the types of parameters that it's going to take. Alright, now with this information, first thing you will notice is that this warning went away, right? It no longer complains about expecting a float over here and that this is not a float. So now what happens when we run this? We find that it actually gives us the correct answer, -1, right? So in other words, it has actually called the correct function, or at least we can hope so, and got back the result that we expect to see, right? So this business of declaring a prototype was sufficient for us. Now what happens is my quad1 was written in another file, arith.c, and my main.c was able to make use of it just by declaring this prototype. Okay, that's looks like good news already. The one catch over there is repeatedly going around declaring all of the function prototypes in many different files. Let's say it's not just main.c, I already have like 10 other files that need to use the quad1 function. I'll have to go and declare the prototype of quad1 in all 10 of those files. Now if it was only quad1, maybe I just go ahead and do it, but there are likely to be maybe 10 or 20 different functions in arith.c. I don't know which ones I'm going to use ahead of time. Should I really go and declare all their function prototypes? No, the obvious answer is that I declare something else, which I call a header file, right? And in this header file, ignore all the other lines that are present, let's just focus on line 3. You will see that it contains a line saying float quad1, float, 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 which is exactly the prototype that we would like to see, okay? Now what I can do is I can go to main.c, and instead of having this prototype here on line 94, I just include a #include arith.h on line 95. Now think about what a #include does. It literally takes the text corresponding to arith.h, right, these 6 lines of text, and puts them in over here. It will expand out this piece of text along with a few other lines with just a hash and a space after them and some text on it, which as we know are going to get ignored by the compiler. So this #include arith.h has not only pulled in a prototype that looks like this float quad1, it has also pulled in a few other prototypes, right? So it's like a nice convenient shorthand to make sure that all the functions that I'm likely to need are captured in one place and pulled in as prototypes. Does this work? Sure enough, right? We find that it does exactly what declaring the prototype explicitly over there also achieved. Now in general, it's also a good practice to go into my .c function itself and also include arith.h over there. Now that's for 2 reasons. One of them is what this contains is a set of prototypes, right? And having the prototype before the function definitions is generally a good idea, right? And what it allows us to do is to basically say that, you know, I have the prototypes declared before the functions. I could also do something like declaring type diffs or declaring some kind of specific structures that are then reused in different parts of this same file. Okay. Now there is one other thing that you might not that you might come across, you are very likely to come across, right, which is this notation that you will find in header files, which is often put in here in order to prevent a header file from being included more than once, right. And it would basically be something like this: if not defined arith underscore h, right, it would say hash define arith underscore h, right. And you would have a hash endif at the end. In other words, what has happened over here is I first check for a parameter arith underscore h. It's just a named parameter, I'm not looking for its value. I check if it has been defined. If it's not, what it tells me is that in this chain of macro expansion that I have done so far, I have not encountered arith underscore h before. I have not included this file ever. But the first time I include it, it promptly goes ahead and sets in arith underscore h. So the next time I try to include it, it will basically just see that parameter, say, okay, I already know all of these definitions, I don't need to include them again, and prevent any possible redeclarations in that chain of macro expansion, right. This is a very common kind of notation that you will find in pretty much any kind of header file that you see, and is a good practice to follow in general, right. And of course, if we run it, nothing changes. It, you know, this has not added or subtracted any functionality from what we had so far. You'll also notice that, you know, the square root of d was complaining about something out here. The way to fix that would simply be hash include math.h, right. And that also sort of shows us one other thing, which is that, you know, there are certain includes where I use what are called angle brackets, the less than greater than symbols. There are other includes where I use the quotes, the double quotes. In general, what happens is that when I am including something from the standard C include paths, I can use the angle brackets. But if I am including something that's currently present in the folder in which I am compiling, I need to use the double quotes. There's no particularly good argument for or against this, right. It's just potentially confusing, right. You sometimes get it wrong and it complains and says, I couldn't find this header file. You need to change the way you put it, but it's just one of those, you know, aspects of the C compiler that you have to live with. But the interesting thing is, the moment I included math.h, that warning about square root went away, right, which is great. Now I don't have any warnings in my code, right, and I find that this behaves exactly the way that I would like. Now there are a few other functions that are present out here, and we'll use them in order to sort of, you know, demonstrate the other aspects, in particular the external variables that we had talked about. Okay. So in this arith.c, I would like to have one particular value, right, or this evar that I have as something that's present in multiple files. So let me first try to declare it in arith.h, right. I am going to comment this out and just basically say float evar is equal to 42. Okay. Does this work? Well, by itself that's not a problem, right, because when I include it in arith.c, it will be okay. It will basically declare a variable. When I include it in main.c, it will be there as a variable. But when I actually try to compile and run it, I end up getting what's called a linker error, right. Now the moment you see this word linker over here, it sort of gives you a clue telling you that each of the individual files compiled fine by themselves. It was when I tried putting everything together that it failed. And the warning that you see is, there is, you know, if you get past all this noise out here which makes it difficult to understand what's going on, you can see that there is one line saying multiple definition of evar, right. In other words, that variable evar has now, according to this compiler, been defined multiple times. Now why did that happen? Because it was defined as a float in the header file. When arith.c was compiled, it set apart some memory for storing evar. When main.c was compiled, it set apart some memory for storing evar. When I tried combining the two together, it doesn't know which one to use. Okay. So what's the solution? Don't directly ever declare a variable inside a header file. That's just going to cause confusion. What you can do is declare the variable inside one of your C source codes, right. It could be in arith.c, it could also have been in main.c, it doesn't really matter, because what I am going to do after that is that in arith.h I will declare it as an external variable. Now what that means is arith.c actually sees two definitions of evar. One of them is this float evar and the other one is an extern definition which comes in through this include arith.h. That's okay, it doesn't get confused, it knows that it has the correct definition of evar and it creates space for storing that variable. Main.c on the other hand does not see a definition for evar. It only sees something that says evar is a variable that has been defined externally. Right now just go ahead and use it as a float, and when the linker gets to creating the executable, it will put everything together and create the space that you need, right, tell you exactly where this variable is to be found. So now with that in mind, right, I can now call a function like this func1 which takes an argument, adds evar to it and returns that value. And if I then go ahead and say, this is what I have, I basically want to print out this value out here. Let's see what happens. I can see that func1 gave me the correct result 52, which is 10 plus 42, and it also printed out the value of evar itself as 42. The extern variable, in other words, worked and was visible both in arith.c and in main.c. But now I have another variable out here called localvar, which I want to use inside func2. I may also want to use it inside some other func1 or func3 or some, so there's a func2 and a func3, both of which make use of localvar, right, which means that it's in some sense a global variable. It's accessible from multiple functions present inside arith.c. But rather than declaring it as static, what I have done is I have basically, or rather than just declaring it as a float, what I have done is I have declared it as a static variable, right. And now when I go into main, what can happen is that the first things first, when I try printing out the value of localvar, you can see that I straight away have an error, and when I try compiling it, it's not going to compile. It basically says undeclared identifier localvar. So that means that localvar did not make it into my main.c definition, right. But if I comment that out, I find that I can run both func2 as well as func3 and they work perfectly fine, right. It prints out whatever the 10 plus 23 and 10 into 23 as the results that I expect to see out here, right, the results of func2 and func3, okay. So in other words, I can use the given variable across multiple functions in this. It is effectively a global variable, but at the same time it is restricted to only this file. It is not automatically visible in my other file main.c. Now one other thing that you can see, just to confirm the distinction between a regular variable definition, the float evar, and the static float localvar, is if you try also declaring localvar as an extern, right. Now what happens is compilation goes through. Main.c does not have any problems with local var. It sees arith.h and it expects to see a external float local var. It assumes local var has been defined somewhere else. But when it actually comes down to the compilation, it says this is a static declaration, right? And it's complaining, basically saying that the static declaration follows a non-static declaration. What does that mean? Arith.c first included arith.h. Within arith.h, I had a non-static declaration, an extern declaration, and over here I have a static declaration, and these two are conflicting with each other. So it basically does not permit me to do this, right? I cannot have an extern float local var out here, which also means I cannot have this definition out here, and as long as I take both of those out of the picture, my code compiles and runs fine. So the bottom line is, this basically tells us about how we can split up the code that we have into multiple different files and try to put the results together.